Ну хорошо, давайте начинать наш семинар. So we should start. So today we have a talk, a new result concerning Dirichlet spectrum. I see uh, uh, specialists not only among the speakers but in the audience also. And so you are very welcome to begin. Okay.
Okay, I will screen now.
You want to share the screen? Oh, it works. It works wonderful.
Can everybody see this
Yes,
share
we
screen?
can see, but we do not see just presentation. We see the file. You can start with just presentation if you want. Well, fine.
Moment.
The first
Uh,
slide. Okay, so you are very welcome.
okay, I think Peng Zixuan will start with the first few pages.
Yeah.
Wonderful.
So, hello everyone. Today, my colleague Wang Siyuan and I, Peng Zixuan, are pleased to present our research on finding the upper bound for the Dirichlet spectrum. Let's look at the second slide. Okay, so our primary objective is to study the continuous part of this spectrum, denoted by D, and specifically to improve the best previously published upper bound for the ray origin constant delta. And to achieve this, we introduce a new Cantor type set, F4 star, defined by some certain restrictions on the partial cotents of its elements. And then we evaluate the thickness of the alternative set log F4 star in order to apply a very well-known sum set theorem to show that the product set F4 star times itself forms an interval. And lastly, we will establish a new upper bound for the delta, which is delta less or equal to approximately 0.94866. Okay, so next slide. I guess we should start with the basics. We'll first.
Yes, of course, you should recall basics for people, for wider audience.
So let's first fix an irrational number alpha, and we will define the irrationality measure function psi sub alpha of t as the minimum over the integer q between 1 and t of the minimum distance of q alpha. And the Dirichlet constant, d of alpha, is defined as the lim sub of t times psi sub alpha of t, where t goes to infinity. And then we can define the Dirichlet spectrum, which is just the image of d over the set of irrational numbers. And then there's a very there's a theorem proved by division of Wang that there is a constant d star less than 1 such that the closed interval d star 1 belongs to the Dirichlet spectrum. I guess we should review some limitations concerning the continued fraction. So for any irrational number alpha, we define its continued fraction expansion as alpha equal to x0 semicolon x1, x2, and so on, where x0 can be an integer and xi, some natural numbers, are the partial cotents. we define the convergence of the continued fraction as follows. So the quotient n over qn is just the continued fraction 0 x1 all the way to xn. And now we consider how continued fractions are related to the Dirichlet spectrum and the Dirichlet constant. Before anything, we have to clarify and define the two terms, so alpha n and alpha n star. We begin with alpha n, which is the infinite tail of alpha. And concretely, alpha n is just the continued fraction xn, xn plus 1, xn plus 2, and so on. While alpha n star is the reversed tail, which is the continued fraction formed by 0, xn, xn minus 1, all the way to x0. And then, with the help of Perron's formula, we can explicitly write psi sub alpha of t only in terms of the continuant of the m plus 1 convergent qm plus 1 and the infinite tail alpha m plus 2 alongside the reverse tail alpha m plus 1 star. And as it's written on this slide, we know that psi sub alpha of t is equal to 1 over qm plus 1 times 1 plus alpha m plus 1 star over alpha m plus 2 for every t between qn and qn plus 1. So from the Perron's formula, we can conclude that d alpha can be written just in terms of rho alpha, where rho alpha, as we define here, is the lim sup of alpha mu plus 1 over alpha nu star, where mu goes to infinity, which can be written as the lim sup of a product. And so in order to study the nature of d alpha, it is sufficient to study the equivalent spectrum, that is the image of rho alpha over the set of irrational numbers, which we denote as overlying gamma. And on the next slide, we'll have to define two constants, and that is delta and mu. So first, delta is basically defined as the infimum of all numbers d in the set of real numbers, such that the interval d1 is included in the Dirichlet spectrum d. And similarly, mu is just the smallest, the infimum of all real numbers z, such that the interval z infinity belongs to overline omega. And it's clearly that the relationship between gamma and mu is that gamma is equal to mu over 1 plus mu, because so in the slide 6, there's the relationship between d and the rho, and if we compute the 1 over 1 plus 1 over rho alpha, we can just see that it's actually equal to rho over 1 plus rho, which is exactly what is written on page 7. So we shall provide some historical context as well. The problem of bounding mu and delta has a rich history. So as we also mentioned, division of Wang proved that mu is less or equal to 12 plus 8 through 2, which is approximately 23.3137. And furthermore, Ivanov has established a I would say a much stronger bound, and that is mu is less or equal to 10 plus 6 over 2, and that's approximately 18.4852. Yeah. So well, what we are doing is to refine Ivanov's approach to the problem and to lower this bound even more. And here we present our main result, and that is the ray origin constant mu satisfies mu less or equal to approximately 18.4811. And consequently, the bound on mu also implies a stronger bound on delta, which is delta less or equal to 0.94866. So our proof primarily relies on a specifically constructed counter-type set. So that's the reason why we have to explain first what is a counter-type set to those who don't know. So a counter-type set E on the closed interval I is defined as E equal to I set minus union of U alpha, where the set of U alpha is just a countable set of mutually disjoint open intervals, which just represent the gaps removed from the original interval. And after considering the counter-type sets, we also have to define what is the thickness of a counter-type set in order to approach our problem. And that's why I would invite Wang Siyuan to continue the second part of our presentation.
Okay, so I'll be defining the thickness of a countertype set. If set E is a countertype set and the order of the intervals U alpha, as defined above, is fixed, then for any removed gap UK, let us denote IK as the largest closed interval in the set before we removed UK. The largest closed interval that contains UK in the set before we removed UK. And we denote by IK1 and IK2 the two neighboring maximal subsegments of IK set minus UK. The thickness of E is said to be at least tau if this inequality, I'll be using a pen here, this inequality holds for all K. Now, the primary motivation.
Wait a second. Why do you say the least one? The least tau?
Wait. Yeah, I believe it was the least one as mentioned in our paper. Maybe we've made a mistake. Wait.
Let us so because you need that all the time for all case what is on the left hand side and on the right hand side of the interval you throw away should be larger than something multiplied by the length of this interval. I am afraid the least will be zero here. You mean the smallest? Probably the
I'm afraid that the list is minus infinity.
Not even minus. Yes. Oh, yes. It depends. It depends. If you think about positive numbers, it is okay. Well, so probably it is a typo.
Yeah, it is a typo. A typo. I checked. I checked the paper. Yeah, it's a typo, and the
And
typo is also.
is it also in the paper? By the way.
Yeah, it's in the
Oh,
paper. We
great,
need to.
great. We found the typo, so it should be corrected.
Okay, yeah. Okay. Uh, okay, so I'm going to continue. The primary motivation for computing thickness is to apply a classical result regarding the arithmetics of fractal sets. which is Hall's theorem proved by Hall Jr. So if E1 and E2 are two counter-type sets defined on the segments A and B, and if both of their thicknesses are greater than or equal to 1, and A and B aren't too different in size, as mentioned here, then their sum set should be a complete interval. And just to clarify when we say the sum of two sets, we mean the set that contains the sum of all their elements, or yeah, the set that contains the sum of all their elements pairwisely. Uh, Now, because Perron's formula relies on the product of continued fraction segments, we'll be applying Hall's theorem to logarithmic sets. For any so we have the following corollary of Hall's theorem. For any counter-type set E defined on a segment A, if the thickness of its logarithmic image is greater than or equal to 1, then the product set E times itself forms an interval.
Oh,
And
by the way, I'm sorry. One comment. One comment. In the paper, it is written a little bit different. It is written that thickness is at least the tau if this happens. So if this happens for tau, sequence is greater than tau. That it's okay.
I believe yeah. Oh yeah. Oops.
This
Yeah, I was just
so
thinking why
this tau is not sequence. Thickness. Thickness is that tau. So there is no typo.
yeah, I was just thinking how
Tau
could we
is
make
the smallest number. Tau is greater than tau from E is greater than tau if tau from E is at least tau if this happens for all case.
yeah, so if tau is negative
So
infinity,
if you look accurately on what it is written, it is not a typo. We do not define the thickness. We define the property. The thickness is at least tau.
yeah.
In this
Yeah,
definition, the following property is defined. The thickness is at least tau. Wonderful. So I'm okay. Okay. So everything is fine. It is.
mm,
It is not a typo. It is just misunderstanding during the talk.
yeah, I was thinking how we could have made such a typo in the paper.
Yes. Thickness.
Okay.
Okay. So you may continue.
Okay, thank you. So I this is I think this is easy to prove from Hall's theorem. So to find our new upper bound, we consider a specific set of continued fractions. So let F4 be the set of all continued fractions, which start with 4, 3, and whose partial quotients don't exceed 4, and which don't contain 4, 4, and 4, 1, 4, 1, 4 inside them. Inside it. Now we will introduce some notation. Let T of A0 to AN denote the minimal closed interval containing all the continued fractions in F4 star, beginning with the prefix A0 to AN. And it should be noted that if a prefix violates the restrictions of F4 star as above, then T of A0 to AN will be the empty set. And we will denote T of A0 to AN lower A upper B to be the minimal closed interval containing all continued fractions in F4 beginning with the prefix A0 to AN and whose n plus second prefix is between n plus second partial quotient is between A and B, which is equivalent to saying what we have typed on the presentation. And we will define yet another notation. We will define Cn as the union of all t's with a prefix of length n plus 1. And we note that the intervals satisfy these t's satisfy two properties, which is that firstly, if two t's with with prefixes of the same length. Two t's with prefixes of the same length don't have exactly the same prefixes, then they are disjoint. And also we can note that it can be noted easily that Cn satisfies this nestedness property, and since the sequence is nested, we can this limit is guaranteed to exist. And now we get to the proposition 2.5 in our paper, which is that C and F for star are identical. And to prove this, firstly, we can note very easily that for every n and x in F4, one must have x included in this T, which is in turn included in Cn. And since x is included in every Cn, it must be included in C. And x was arbitrarily chosen, so F4 star must also be in C. And it remains to prove the reverse inclusion. Now we assume by contradiction that there exists some x in C but not in F4 star. So for every F4 star, we can x not in F4 star, we can define this integer value, which is just the first index in x's continued fraction expansion, which violates a rule for F4 star here. And this, since x is not an F4 star, this k of x is well defined and finite for every x not an F4 star. However, x is contained in C, so and C is made up. So for arbitrary I, there is a unique and C is contained in every Ci. So x is contained in every Ci. For every arbitrary I, there's a unique t with a prefix of length I plus 1, which contains x. And if we take I equals kx plus 4, we see that there is a unique interval t with prefix length kx plus 5 that contains x. And since x has the prefix of the kx plus 4 prefix of x is this, we see that x must be contained in this t. But now we note that this t is an empty set because no element in F4 star begins with this prefix, and this contradiction completes the proof. We will try we can see that F4 star has a fractal-like structure, and we think it is a Cantor set. So to prove this, we will construct two infinite families of intervals for any non-negative integer I. So first are the segments, and second are the gaps, which are the intervals that we will be removing from the Cantor set. So the base case is I10, which is defined as T43, and that is this interval. And to clarify, by this interval, we mean the interval starting with the continued fraction 43141413 repeated and ending with 43414131 repeated.
So it is not necessary. So one question: it is not necessary. So you have here. Look. You have here a lower index and an upper index, and
Yes.
it is not necessary that the lower is smaller than upper. It depends on parity of the place where we have this determination, isn't it?
Yes. I think this is a
These are just endpoints. Endpoints.
yes. Yes. These are just endpoints. I think we will make a note of this a little bit later. I think that in this case, it is indeed the case that the lower bound is the smaller one, upper
Because
bound is the larger.
the place the index of this place is even.
Yes. I think that in this case, yeah, it is indeed the case. The lower one is the smaller one. Okay. So for I greater than or equal to 1, we will define aij inductively from aji inductively from aji minus 1, according to the rules on page 22 and 23, which we will talk about shortly. And we let the gap GJI be the parent interval subtracted by the set minus the union of the two children intervals. We let cursive AI be the union of all the AJIs on the level I, and we let cursive A be the intersections of all the cursive AIs. Uh, and we and it can be seen from the rules that we will describe just a bit later that AI plus 1 is contained in AI because our algorithm is by partitioning each the two children intervals are contained in the parent interval, and so this is this expression can be true, and the limit. And since this expression is true, the limit of all the AI exists, and that is just equal to cursive A. And we note that intuitively we can think of a cursive A as being constructed by starting with A10, the base case, and throwing out the segment GJI at every step. And Peng Zixuan will continue this presentation for the next 10 pages.
Okay, so since Siyuan has talked about the division algorithm, I will be speaking in more detail about how our algorithm actually works. Before that, we have to classify every type of segment that we might face during the process of departitioning, and we have successfully categorized them into 9 types, and they're all represented in this table. It might seem very complicated, but let me explain. The way we decide the type of one given segment is that, let me make some notes here. How can I draw one? Okay, so say we're given a segment, and we know the exact continued fraction expansion of its endpoints. Now, how can we deduce its type? So our thinking process is as follows. We will first, okay, so let's say we look at the left endpoint, and what we're doing is to look at the last partial quotient before the continued fraction enters the infinite loop of its period. So I'll give a concrete example. So let's say the left endpoint that we're dealing with is something like, so it's actually terrible, I cannot write properly on my computer. Let's say it's something like 4, 3, and 1, 4, 1, 3, pardon, 1, 4, 1, 4, 1, 3 in repeat. Okay, so something like this. Excuse me for the terrible handwriting. So let's say this is the continued fraction that we're dealing with. Now, let's check the last digits before entering the before entering the infinite period of 1, 4, 1, 4, and 3. And of course, it's 3. So the last digit is 3. And according to this table, because it is, before the last digits are not the specific, are not some specific patterns like 4 or 4, 2 or 4, 1. it is so this continued fraction is one. It must be one of the types of actually no. So what I'm trying to say is that the first the first endpoint, 4 3 1 4 1 4 1 3 in repeat, it's sufficient to categorize the segment in one of the three types. So so the segment is either type 1 or type 3 or or type 2 or type 3. In order to deduce the exact type of the segment, we have to look at the other endpoint. And depending, it's the same procedure. And depending on the last digits, on the last partial quotients before the period, we can deduce whether it's type 1 or type 2 or type 3. So shortly, this is how we clarify every type. We just look at basically the tails of the continued fractions of the segment's endpoints. Now I would like Wang Siyuan to turn the page, and on the next slide we have some.
I think we need to erase the annotations, but yeah.
Okay, so on the next page, we will be looking in more detail at each types. So here we will take type 1 as an example. So as the title also suggests, so type 1 is associated with rule 1. And it's very clear that generally type I is associated with rule I, and for each type, so let's say we have type I, then we have to apply rule I in order to divide this segment into further children. So to continue, so we apply, so basically for the segment of type I, we apply rule I to continue our indefinite division process. And so as for our first rule, we will divide the interval that is of the, that looks like, it's like, if our segment has the endpoints with the period 1 4 1 4 1 3 and 4 1 4 1 3 1, while the last partial quotients before entering the period, and that is so an minus 1 and then an minus 2, they did not form some specific patterns, then it is of type 1. And for this type 1 segment, we apply rule 1. And the division process is illustrated in the following diagram. Because as Siyuan introduced earlier, each type of segment.
By the way, do these objects coincide? For instance, you have this A with indices, and you have this T. Are these two segments just the same ones?
You mean, are they? So the two objects that you circled are, I believe they are indeed the same one.
Because the first one is just determined by its endpoints, and the second one means that we consider our set, what the elements of our set which fall inside this cylinder, which have the same beginning, which have this beginning, and the last partial quotient is between 1 and 3. So you claim that this segment, which is defined in some sense in explicit way as just the set of all elements of F which fall into this larger interval, this explicitly can be written as this A. This is the statement.
Yeah, so basically T, so what we defined earlier as T's are basically some alternative characterizations of some segments. So in this case, TA0 all the way to AN of
So
3.
all T's are in fact A's.
Uh,
So this
are,
T
there,
is
yeah,
also this A, isn't it?
yeah, they do represent the same set.
Okay. Okay.
So, as the diagram also suggests, more concretely in our type 1, we'll divide TA0 all the way to AN into these two following T's, which are um, which are of the type 2 and 4. And so on the next slide, we'll be discussing a similar case, and that is type 2. I would say that the division process is somehow they're very similar. So say we're given a type 2 segment. What our algorithm does is to divide it into two smaller segments. So it divides this type 2 segment into one smaller segment of type 3 and the other one of type 1. And the division process is also illustrated in the diagram. It's basically the same procedure really as with what we saw in the previous slide. And as you may imagine, the 7 other rules are basically, in some sense, just very similar to these first 2 rules that we have discussed, but we cannot really enter in much detail because we don't have much time reserved for this. And I would say they're just some technical parts. So I guess we should really focus on the main parts of our proof. Yeah, so let's look at the next slide. On this slide, I guess we should first explain our subdivision rules further. So each type follows a specific rule, as I said, to divide them into 2 children of other types. And so, for example, if we have a type 1 parent, we then split it into type 2 and type 4. And we have proven that our process continues indefinitely because each type of segment is just transformed into other 2 types which are already categorized. So the process will continue indefinitely. And the reason why we consider these A's and T's to divide our counter set is because we can prove that they indeed represent the same object, and that is A is equal to C and is further equal to F4 star, where A represents the I'll say is the yeah, and I mean we have defined earlier is the limit of an where n goes to infinity, and C we'll just recall the definition is the limit of Cn where n goes to infinity. So they basically represent the final I would say product that we get after going through this infinite process of division. And so with this lemma, we can evaluate more easily the thickness of F4 star with some estimation tools. And this is what we're going to talk in the next slide. So in order to prove a Okay, so let's remember that our ultimate goal is to prove that the thickness of the log set, so tau of log 4 star is greater than 1. But this is a harder thing to do than to evaluate tau f4 star. And actually, evaluating the thickness of the original set f4 star also helps proving and actually finding the lower bound of the thickness of the log set. And so that's why we have to first estimate the thickness of the original set f4 star. And to do so, what we're doing is to compare the lengths of the gaps Gij and the neighboring child intervals and compute their ratio. And in explicit terms, the length of any interval t of a0 all the way to an of ab is given by the following formula. And it might look a bit scary, but if we use the ratio of epsilon n to denote the quotient of continuance qn minus 1 over qn, we can simplify this by a lot. And as you see, it has a very simple form, and then that is t is equal to the modulus of b minus a over qn squared times some two other terms. And we have to also mention that a and b here actually represent, they do not represent the single number. They represent the tail, actually. But they are explicitly defined after considering the t's. So there are some constants in our following computations. Let's continue. With the next slide. Sorry.
Can I just mention that there is a tiny typo here, because A and B are continued fractions. It would be better to write this.
To write parentheses, yeah.
Right.
We can also write
Yeah.
parentheses, but
What's the matter? I do not understand well what.
So Siyuan thinks we should also write parentheses for these B and A's, which would actually represent some tails. But I think it's somewhat understandable. Like if they
you want to write B, B.
parentheses.
Well. Look. Wait a second. What is B? B is not an integer here.
Yeah, B represents the tail, so it's
But then this notation seems to be okay because B is a real number.
B, I think it's better to say that B is a string, because B is here, here. Yeah, B is a string, so string of continued fraction things. So a string of partial quotients. So
B
yeah.
has infinitely. B is something I can write. B is equal, then this, then one partial quotient, another partial quotient, yes,
Yeah.
another partial quotient, and so on. So it is just a real number.
Yeah. Okay.
so what Siyuan actually
So
wants
you
to
can write here just B, because if you write this, people may think that it is an integer part, and it becomes worse. It becomes worse.
Okay.
Because here it is clear that B here is just a value of a continued fraction, because in the very beginning, when you considered for instance segments, you write here so as subscript and superscript indices continued fractions. So it is not there is no problems with notation. So this B without any brackets agrees with notation.
Okay, then I'll just have to clarify the notation below because we're using parentheses.
Here it is worse because
Yeah.
look, these things look like integer parts.
Okay, yeah, I guess we'll have to
It is
delete
better.
them.
It is better. Or infinite blocks. Here you define infinite blocks. You mean that infinite blocks. Infinite. It means something like tails.
Yeah, yeah.
I think here the definition of ABCD are that they represent the sequence inside the parentheses. So, Professor, you mentioned that
You mean that this is a sequence? So A without parentheses is a sequence, and this is a value of continued fraction.
Yeah, but if it's
But if it is
yeah,
written in such a way as it is written here, so it is quite common to understand that it is integer part. So it is, this notation is not very good.
then we'll just change it to ABCD are the tails of
I think you can add here words, a sentence with explanations. So we denote by the same letter the value of if A is equal to A1, to see if we consider sequence A equal A1, A2, and so we denote by the same letter the value of continued fraction.
Okay.
It is
Okay.
better to if you want to make something more explicit, you should write something like this. So if we consider a sequence A, an infinite sequence A, which is equal to A1, A2, A3, by the same letter we will define the value of continued fraction A1, A2, and so on. I think it is better to avoid these notation without explanation, because it looks very likely very similar to integer part.
Okay. Then we'll just change this in the
So
paper.
I think without brackets, without parentheses, it's it is a little bit more clear.
Okay.
Okay, fine.
mentioned on the following
Continue.
slides. Okay. So I guess we shall continue, and let's recall that what we're actually interested is the ratio between the gap and the neighboring segment, and in in words, it's actually the length of G gap over the length of A child, where A represents one of the neighboring segments of G. And with the previous formula that we deduced, we can express it only in terms of the tails of the gap and the child alongside epsilon n. And so
Just one more comment. I think I looked one more time into the paper, but in the paper it is clear. I think you may not change this parenthesis, because it is written explicitly and everywhere. So if blocks, then you consider continued fractions. Maybe at the end of lemma 2 just add that by this brackets you mean the value of continued fraction, to make more clear. I think it is not, there is no necessity to change in the paper everywhere to delete brackets, you see, because they are everywhere and they look more or less nice. but just to be sure, to avoid misunderstanding, I think it is better to give one sentence in, say, in lemma 211, that this bracket means here the value of continued fraction with this infinite sequence. Okay?
Okay. So we should add a explanation to
Wonderful. Okay.
applications.
Well,
So let's continue with our estimation. What we're interested to do is to bound this ratio of G over A. And we see that if we can control epsilon n well enough, then of course we can also bound this term. We then try to find some inequalities that can bound epsilon n in order to find our the bounds that we're actually interested of. So using the recurrence of the continuance, we can see that epsilon n is equal to 1 over an plus epsilon n minus 1. And so with this relationship, we can bound epsilon n with 1 over 5 and 1. And so maybe I should explain this in a little more detail. Since we know that an is a partial quotient, so it's it's a natural number. So it's larger than 1, it's larger or equal than 1. And epsilon n minus 1 is just a real positive number, so it's larger or equal than 0. And that's why we can bound epsilon n by 1. And similarly, for the lower bound of epsilon n, we can bound an by 4 because we know that an is a partial quotient of an element that is a part of F4 star, which we know that every element in F4 star has partial quotients between 1 and 4. And since we have deduced the upper bound for epsilon n in the previous inequality, we can bound epsilon n minus 1 by 1. So the whole expression, so epsilon 1 will be just greater or equal than 1 over 4 plus 1, which is 1 over 5. And so after establishing the bound on epsilon n, we can now bound easily the ratio of the gap, the ratio between the gap and the neighboring segments. So we apply the bounds that we obtained on epsilon n successively, and we can see that the ratio between the gap and the left neighboring segment is the expression here, a plus 1 times c minus b over exactly that expression. And similarly, using the lower bound on epsilon n, we obtain a similar result regarding the quotient of the quotient between G and the right neighboring segment. So using these inequalities, we can perform some computations of the 9 types to deduce the upper bound, which is actually a pretty good estimation of the thickness of the Cantor type set F4 star, and that is our corollary 2.13. So this result says that maximal value of the ratio cannot exceed 0.9834. But let's recall that the thickness is the minimum value of the ratio between between the neighboring interval and the gap. So it's just the reverse of what we have computed earlier. So that's why the thickness of F4 stars must satisfy the tau of F4 star is greater or equal than lambda 2 minus 1, which is just a constant slightly larger than 1. And until here, we have finally proved that the thickness of F4 star is greater than 1. But we cannot stop here because, as I said, what we are actually interested in is the thickness of the log set. So we have to continue by proving the thickness of the log set is also larger than 1. And in order to do so, we have to use a lemma. It's in our paper. It's lemma 2.15, and it's basically it provides some useful qualities to verify and to compute the thickness of the log set um, only knowing the structure of the original set. So what I'm saying is basically if we are given the exact form of the neighboring intervals and the gap of the original set, we can use lemma 2.15 to eventually compute the thickness of the log set. So we'll explain in more detail in the next slide. The proof of the lemma, we will not discuss it in very detail here because it's just some computations and some algebraic manipulations. But its consequences are quite significant because we can use the lemma. Okay, so because we can use the lemma to verify that that for every pair of index ij, the lengths r, s, and t of the subdivisions of the segment A0 satisfy the formula star, which is just in the previous slide. It's a huge inequality. This lemma also suggests that in order to bound the thickness of the log set, it is sufficient to verify the cases when the neighboring segments have the neighboring segments have a length less or equal to a certain value, and I believe it's around 0.07, 0.07, yeah, exactly. But since by our construction of the Cantor type set, we know that, please go to the slide 32, I think. Yeah. So because by our construction of our Cantor type set, we know that any subinterval's length will not exceed the length of the segment that we began our division process. So basically A0. And a computation shows that the length of A0 is around 0.05, which is less than 0.07. So in fact, there will be no cases that we have to check because as I said, no segments have length larger or equal than 0.07, so we don't have to check anything, and it is guaranteed that the thickness of log set will also exceed 1 due to the lemma 2.15. I think maybe Siyuan should continue with the rest of the proof.
Okay, so now, after all of these tools have been introduced, we can finally get to the home stretch of our proof. Now we prove the main result, and we state the main theorem here again for convenience. So now since we have the thickness of log of FR star greater than 1, the product set of FR star with itself is now an interval, and it is this interval. And clearly we have that the interval from this number to 10 plus 6 root 2 is in this product set. So we know that any number alpha in this interval will can be represented as the product of two elements in F for star. Uh, Now we will try to uh, construct a number x such that the Dirichlet constant of x is exactly alpha. So to do this, let Ni and Mi be two infinite strictly increasing sequences of natural numbers, such that Xni and Ymi are both not 4 for all I greater than or equal to 1. And since in F4 star, no two fours can repeat. There can't be any consecutive fours. There will exist such sequences. Now we can let Si, this block Si, be defined like this. Uh, uh, Wait. Yeah, we'll let Si be defined as so. And let let X be a concatenation of all the SIs in order. And for convenience, we let SI star be SI the reversal of SI. Now we introduce the notation. For convenience, we introduce this notation. Rho n of a continued fraction is rho okay is simple. Oh, sorry. Yeah, this is hard to write on. Uh, oh, okay. I'll just use this pen. X0, X1. In It'll be simply this continued fraction divided into two, and we read this part of the fraction from right to left and this part left to right and multiply them together, which gives this. Now let Ki denote the index in the continued fraction of egg. Sorry, wait for me a moment. Continued fraction of x that corresponds to the occurrence of the element uh x0 here, here, x0, from the block Si. We observe that the limit as I approaches infinity of rho ki of x is alpha. Now, to continue, we will first demonstrate that the string 414 does not appear within the continued fraction expansion of x. By construction, the string is absent from the block x0, x1 to xni and y0, y1 to ymi because these are both in F4 star and F4 star cannot contain 414. Because 4 is palindromic, it must also be absent from the reversed block here. From the reverse block here. Um, and furthermore, the string cannot be between the junction of two adjacent blocks. It cannot span the junction x0, y0 equals 4 because 4 and 4 and 4 does not have consecutive 4, so it can't be x0 between x0 and y0, and it cannot be between ymi and xni plus 1 because this string 4 and 4 and 4 alternates between 4s and non-4s, but ymi and xni plus 1 are both not 4. So now we consider any sequence of indices ki prime that shares at most violently many terms with ki. And since in both x and the reversal of x, there can't be a 4 on 4 on 4. If we read the continued fraction of x backwards from here, there can't be a 4 on 4 on 4 here. And if we read it starting from here and behind there can also be a 4 on 4 on 4. Since there are no consecutive 4 4s, either this is 4 and this is 3, or this is 3 and this is 4. So if this is 4, then the largest this part can be is, well, 4 1 4 1, and then of course we can't have another 4. There isn't any there can't be a 4 and 4 and 4 pattern here, so it must be 3 and 1 3, and then of course there's a 1, and if we continue this, it will repeat itself. Starting from 3, we have 1 4 1 4 and 1, but then it can't be 4 again, so it must be 3. And this will repeat itself. So we see that this holds, or if 3 is here and 4 is here, then this holds. And from this, we can see that the limit supremum of pki prime of x, where ki prime is shares at most finally many terms with ki, meaning that at some point it won't share any terms with ki anymore. The limit supremum of this is at most the product of these two numbers, which is less than alpha. And it follows that alpha is the limit of this peak row ki, or sorry, row ki of x, and that is the limit supremum, because the other sequences can't exceed it. And this is just row of x, and that is in omega bar. Since alpha was chosen as an arbitrary element of this interval must be a subset of omega bar, and this completes the proof of our main theorem. Just wait, these. Now we can return to the standard Dirichlet spectrum. Remember that on page 7, we deduced that delta is equal to mu over 1 plus mu, and if we substitute our new upper bound, we get the improved bound for the Dirichlet spectrum, the ray origin of the Dirichlet spectrum. So to summarize, by Perron's formula, we converted delta into mu, and double D, the Dirichlet spectrum, into omega bar, and we defined a countertype set whose elements have continued certain restrictions on its continued fractions. We then proved that we then turned F4 star in. We can then constructed F4 star like a countertype set, and thus proved that its logarithmic thickness is greater than 1, and which in turn gives us that F4 star times itself is an interval. And by using this, we lowered the ray origin to our current record. And this is the end of our presentation. Thank you for your time and attention, and we're sorry for any mistakes that we may have made in the process.
Oh, thank you very much. I hope there were no mistakes. So we did this. There was some misunderstanding, but well, So thank you very much for very detailed exposition. So of such an interesting result. So any questions, comments? То есть если какие-нибудь вопросы, высказывания. So I want to ask what, how do you think, where is the exact value of the beginning of the array? How do you think? So of course you do not know it, but what is the impression? In what you believe? Where is it? Is it close to this 18 or far from 18, much smaller than 18? What is your feeling?
I hope it's close to 18.
Close. So the bound is rather close to optimal.
Yeah, I actually have a quite different opinion on this. I think, I mean, I don't have any rigorous arguments, but it's just based on the feelings. I just think the true origin of the spectrum I think it should be far less than 18, maybe even less than 10. And I also think that um, the way we approach the problem by using Cantor typesets may not be the way that can really tell us the final answer, because
Oh,
I think it's not the right method that we should apply for
oh,
this.
you think that it is not the right method?
Yeah.
Oh.
I think there should be better approaches.
I agree with this. I think it's really just far from the best method because Ivanov got the best. I think he got the best out of this method by just adding 4 and magically reducing the limit by 6. I think yes, 5. But then we by adding 4 and 4 and 4, we were thinking that 4 and 4 works, but then its thickness is not greater than 1. Maybe it still satisfies that its product set is an interval, but we don't know. Maybe 4 and 4 works, but even if it works, it can't lower the bound much more. And if the bound is even 15, then this method by using counter typesets will just fail completely. So I think the final solve for this will be topological, but yeah,
Oh. It's very interesting. By the way, I want to give a comment that now several interesting results appeared related to various spectra. So the Dirichlet spectrum is not the unique spectrum under research. Quite recently, Nikita Shulga proved something very interesting about another so-called Minkowski spectrum. And now I have no idea what is the right answer. Where should be the right answer here? By the way, I want to ask you one more question. So, are you able to prove that in Dirichlet spectrum there is an interval, the whole interval, which is located somewhere in another place, less than your value, 18 point something? Can you observe an existence of an interval somewhere below 18?
We didn't research this. I think Ivanov in his paper in 1980 observed like an interval somewhere, but yeah, we didn't put any effort into this.
I see. But there are. You remember that Ivanov had something on this question. Something was
Yeah,
able
I
to
do
answer.
remember this. I think I do remember this part. So from the Ivanov's paper, we know that there is a gap at around 5.8. And what we have done is to prove that the ray origin should be less or equal to 18 point something. But Ivanov also pointed out that there is certainly a gap.
A gap, yes, yes.
A gap.
Gap. It means that there is a gap. It means that it is a lower bound for the beginning of the ray.
Yeah, and in
Yes.
fact, from what I heard from the fellow researcher, I think there's also a bound at around 7.25. So clearly, this ray origin constant cannot be lower than 7.25 because there's a gap there.
Yes, yes, I remember the statement about a gap. Yes, yes, I remember it. But as for the whole interval different from this, I don't remember if there was such a statement in Ivanov's paper. Okay, any more comments, questions, remarks?
Professor, I would just like to take this chance to ask you if you knew Ivanov, because we are very curious as to who he is, and
No, I
we
don't know. I don't know him. There are some, although I worked in Moscow, I don't know him.
uh, he doesn't appear in the mathematics genealogy project, and we can only find his name in some like obscure Russian website.
Unfortunately, a lot of interesting mathematicians are not presented in mathematics genealogy project. So maybe in some future, maybe he had no students or something else or something else. There is a lot of good mathematicians which are not mentioned there. So I am trying to add, from time to time, I am trying to add something to mathematics genealogy. Yes, it is
Oh.
a very nice and interesting project. So, but by no means it is complete.
And I think I was under the impression that Ivanov was a student of Ivan
No,
Vinogradov.
I don't think so. I don't think so. Vinogradov was, first of all, Vinogradov. Oh well, okay. This is another story. I think we should stop recording. So thank you very much.